Thank you very much. First of all, I'd like to express a sincere thanks to the organized committee of inviting me and gave me a chance to present our recently investigations. The title of my presentation is Ion Image Sensor based on CCD and CMOS technology. This ion image sensor is a result in a fusion of sensor technology and LSI technology. Here is the outline of my presentation. At first, I'd like to explain the background of motivation why we start the developing of ion image sensors. Next, I will explain the principle of the CCD type ion image sensor. And after that, I will show some results, application results for biomedical field using the special ion image sensor. So one is the observation of the real-time observation of the apoptosis in a hippocampus, and another is acetylcholine real-time imaging from the neural networks. Finally, I will conclude my presentation. The demand for biosensor has steady increase in various fields, such as biochemistry and medical diagnosis and agriculture. So we have been developed a smart biosensor, which is integrated LSI and sensor in the same chip. Then this smart biosensor reads a highly sensitive device, compact measurement system, and also developing a new novel devices, which is not realized yet. So my ion image sensor, our ion image sensor is one of the novel devices result in LSI technology and biosensor technology. This is a movie of the microorganism taken by the conventional optical microscope. Medical doctor use this microscopy to understand or to analysis of the microorganisms. But we can only understand the shape and movement by the optical microscope. So if we have a special microscope, which can be catch a chemical reaction or chemical activity in microorganisms, we can understand a lot of unknown phenomena by the special microscope. This is commercialized pH sensors. As you know, the pH sensor measures the pH value. And this condition, we assume these solutions have a uniform concentration. So if we can, by using the LSI integrated circuit technology, if we integrated a lot of micro-size biosensor in the same chips, we might be catch chemical reactions using the solid state type devices. So that is the motivation to investigate or developing the ion image sensors. I believe the optical sensor is a sensor with highest density and refined process. This picture is the pixel structure of the optical image sensors. Most recent image sensors have the pixel pitch is 1.4 by 1.4 micrometer. So let me superimpose the human cell on the sensor chip, like that. So the diameter of the human cell is about 20 micrometer. It means there is a possibility to catch chemical reaction or chemical situation of the surface of the human cell, like that. And of course, optical sensors have a sensing area and reader circuit. So instead of the optical sensor, we fabricate in a biosensor in this area. This is a fabricated ion image sensors. So here is a sensing area for pH, hydrogen ion, and these are readout circuit. And pixel pitch is 23 micrometer, and sensor area size of the sensor area is 3 by 3 millimeter. I will show you the real-time ion image later, but we can get a very clear ion movement by the ion image sensors. Firstly, I'd like to explain the principle of our sensors. So as you know, ISFET is very famous solid-state type pH sensors. Our proposed CCD type ion image sensor has same sensing structure. The sensing area consists of electrolyte, sensing insulator as a sensing membrane, and semiconductor. The electrochemical potential between electrolyte and insulator is changed by the proton ion, hydrogen ion concentration according to the Nernst equation. Then this chemical potential changes is the chemical potential is affected the potential in a semiconductor under the sensing regions like that. So that the potential depth of the potential changes of the in a semiconductor is converted to the electron quantity by using CCD technique. I will show later. The maximum sensitivity of the maximum change of the sensing region of the potential is 59 millivolts per pH. So it is a little bit hard to catch these small potential changes. But so I will show the schematic movie to explain our devices. As you know, the conventional image sensor is catch the electron, photo-generated electrons under the sensing regions. And these electrons are read out by the conventional CCD technique. On the other hand, our proposed sensor so conventional photo CCD image sensor is catch photo-generated electrons. On the other hand, our proposed sensor, the proton ion concentration is changed to the depth of the potential well. Then we have to change the electron quantity. Depth of the potential well have to change to the electron quantity using field and spill technique. It is classical technique for the CCD researchers, just like fill the water and read the measure the quantity of the. To understand the depth of the potential well, at first we fill the electrons. Then this electrons is corresponded to the pH value, so we read out the electron quantity by using CCD technique. I will show the basic operation. Our CCD image sensor, CCD type ion image sensor is have two extra gate, ICG and TG, from the ISFET. Then the potential of this area is changed by the ion concentrations. And after them, firstly, the input diode is briefly pulsed to VID2. Then electrons are filled under the sensing region, flow into the sensing region, and kept again VID1. So electrons are remained, which is corresponded to the pH value. And these electrons are read out by the to open the TG. Then this potential changes are read out by CCD technique or image sense technique. And our sensor have a very good, unique features. So the charge accumulation operation was repeated several times. Once, twice, third. The charges is increased proportional to the repeated cycle. It is very similar for our digital still camera, because when a dark condition, the shutter time is changed by the condition of the condition of the light conditions. So then these the photogenerated electrons is accumulated under the sensing region. So our sensor also can be accumulated in a sensing region. On the numerical analysis, signals is proportional to the repetition cycle. And noise is written by the root n1 square plus n2 square plus nn square. If these noise components are same, the noise is written by this root n0 square. So as you can see, the noise signal to noise ratio of this device is increased in proportional to the root n. So this is a mechanism why our sensor can get a very high sensitivity or very low noise. This is a result of the experimental result of the charge accumulation operation. We prepared 6.86 and 6.94 solutions. The difference is only 0.08. So in a commercialized pH sensor has minimum resolution is 0.1 pH. So it means it is very difficult to distinguish these two kinds of solution. But as you can see, as increasing the accumulation cycle, the difference from the output signal from the two solutions is clearly. It is about 25 millivolts. So from this result, we can suppose the minimum resolution of the sensor is about 0.001 pH. It is the highest resolution in pH sensors. We expect it by using this accumulation operation, we can catch a slightly change from the human cell or something like that. Then we also check the equivalent noise. This axis shows the accumulation times, and here is the noise power. On the no accumulation conditions, the noise component is same as ISFET. However, increasing the noise accumulation times, the noise is drastically decreased, and on the 5 times charge accumulation, the noise is decreased to the half. Okay, now I will show a movie of the charge, ion image taken by the ion image sensor. The frame rate, maximum frame rate is 58 frames per second. It means the time resolution is 70 milliseconds. The number of the pixel is 16,000 pixels. And then pixel 23 by 23 micrometer. Here is the pH images. And also, our sensor is based on a CCD technique. We can catch optical image simultaneously. So optical image shown here. We drop the pH pH 7 solution onto the sensing region, which is covered on the pH 9 solution by the pipette. So you can see the pipette tip of the pipette from this in this images. The pipette and another pH solution is emitted. Like that. There is no label, no color. We just take the pH, proton ion concentration catch at real time. Then you can see a very clear. This is pH images. This is 70 millisecond time resolution, like that. So by using the special ion image sensor, we have some collaboration work with medical field researchers. This is collaboration work with Hamamatsu Medical University. So they put the hippocampus on the image sensors. The hippocampus, as you know, the hippocampus is a key part of the our memorizing of the memorizing. But when we choked, the memory is temporarily disappeared. So this experiment is simulated these conditions. Then, the medical researcher said, it is wonder, in the hippocampus, only a very special part of cells of the special part is death. But even if the whole area of the hippocampus is have a stress, then then they carried out this experiment. They put the sliced hippocampus from the rat. Here is a CA1 area and CA13 area. They put the 0.1 millimolar glutamate. The glutamate is simulated the stress. Then, as you can see, here is a hippocampus. The hippocampus is alive, so alive and breath. So pH is decreased gradually. On the other hand, 1 millimolar glutamate stimulation, here is CA1 area. Only CA1 area's pH is drastically decreased like that. But CA1 area's pH is not decreased. So the medical doctor often said, only the CA1 areas, cells of the CA1 area is died. So this experimental show the first movie image of the real-time situation of the cell die. And we tried to observe acetylcholine by using the hydrogen ion image sensors. The acetylcholine is a very famous and very key neurotransmitter for the neural networks, neural cells. Then the acetylcholine concentration is very affected the Alzheimer's disease. So if we can catch the real-time image acetylcholine emission from the neuron cells, if we can catch a neural acetylcholine emission, it might be get a good information for to solve the Alzheimer's disease or something like that. And also, the acetylcholine, there is no fluorescent survey for acetylcholine imaging in present time. So it means it is very difficult to get a real-time imaging of the distribution of the acetylcholine at that time. So we employ the enzyme reaction on the surface of the proton ion image sensors, hydrogen ion image sensors. If we immobilize the acetylcholine esterase on the sensing area, then when the acetylcholine is coming to the sensing area, these enzyme reactions will be occurred and protons are generated. So our sensor catch a proton, then we can catch an Alzheimer's coming condition. Then we employ the polyion complex membrane to immobilize the acetylcholine esterase. This polyion complex membrane is very good materials to high acetylcholine with high density. This is experimental result of the real-time imaging of the acetylcholine. Then 100 millimolar acetylcholine are dropped these areas. Then the acetylcholine is diffused in whole areas. So we can understand we can catch the acetylcholine diffusion directly without label. Then minimum sensitivity of the acetylcholine image sensor is 20 micromolar. Then this value is not so enough to catch a neurotransmitter, because from our neural network, neural cells, about 10 or several micromolars acetylcholine are emitted. Then this value is not enough, but we try to catch acetylcholine by using the ion image sensors. So at first, we cultured the neural cells, which is taken from the rat hippocampus on a collagen sheet. collagen sheet is often used as a substrate of the culture. Often used as a substrate of the culture. Then we use the cultured human neural cells after 3 days cultivation. Then this collagen sheet is put on image sensors, and we stimulate the potassium using the potassium stimulation at the side of this here. Then we expect it. The acetylcholine release will be observed near the potassium stimulation area. And as you know, our neural cells have a network each other. Then it might be catch the neural communication by using some. If we catch the acetylcholine emission from there, it might be catch the acetylcholine emission by the neural communication. Then we try to this experiment. Here is a ion image sensor, and this is a chamber. This is the results. We put the potassium KCl gel on this area. Then, so by the stimulation, we can catch acetylcholine emission from here. And this emitted, the stimulated area's acetylcholine concentration is rapidly decreased by the potassium stimulation. The acetylcholine emission is rapidly increased and gradually decreased. And here is the stimulated area. Then, but we can see some slightly the acetylcholine emission is observed here. So, so it means this result shows some possibility of the image sensor possibility to catch the acetylcholine communications. But we need more further investigation using this image sensor to discussing more medical field with medical field researchers. Okay, I will conclude my presentation. So I believe this possibility, the application area of the ion image sensor is infinity. Then I discussed with medical field researchers. They proposed me, please attach the ion image sensor on the endoscope. As you know, the cancer cell is more active rather than normal cells. So the medical doctor says it might be observed of the humans of the cancer cell directly. And and also we talked with the chemical material researchers about for the application of these sensors. So they suggest me small-sized materials, which is ion transportation material. I'm not sure, but there is no. It is very difficult to observe the ion transfer phenomena in a small size. So it might be observed by using sensor. But anyway, so I am an electron device researcher. So I don't know where is the most important application. Then I'd like to say for the other field researchers, please use our devices as you like it. That's all. Thank you very much for your attention.